In this lesson, we will discuss contour integrals. Now that we've defined integrals of complex valued functions of a real variable, and we've discussed contours of integration, we are ready to define integrals of complex valued functions of a complex variable. Let's start by letting C be a contour be defined by the function z of t for t between a and b, and suppose we have a continuous function on the contour C. Suppose the function f is continuous on C. Then we define the line integral or we could just simply call it the contour integral of f along C in terms of the parameter t. So we'll write the integral of f on the contour C by putting the C below the integral sign. So we're going to define this contour integral as an integral of a complex value function that we've done before by using the parameterization. So it's going to be the integral from t goes from a to b of f of z of t times z prime of t dt. So we're going to substitute in the parameterization z of t for z, and we can evaluate this function as a function of a real variable that is complex valued. So in future lessons, we'll look at evaluating contour integrals using antiderivatives, but if we have a parameterization for the contour, we can evaluate it this way. A couple of notes about this definition. The integral will depend on the points of C, so it depends on the contour C, as well as the direction of the contour. So if we change the orientation of the contour, that will change the value of the integral. So this integral depends on the points of C as well as the direction. So the orientation of the contour makes a difference. So while the integral depends on the contour C, it's actually independent of a particular parameterization of the contour. So this integral is independent of the particular parameterization. So since these contour integrals are defined as line integrals using the parameterization, we can use several of the facts that we used for integrals of complex valued functions of a real variable. So some of the facts that just follow from this definition of the line integral. First, if you have any constant, any complex constant z0, and we have a constant inside the integrand, so we take the contour integral of z0 times f of z dz over the contour C, we can factor out the constant z0 Secondly, things like we have the constant multiple rule, we have the sum and difference rule, so the integral over the contour of the sum f of z plus g of z, we can break this up as the integral of f over the contour C plus the integral of g over the contour C. So given a contour C, we said that the orientation matters. So if we take any contour C, then we will denote the curve negative C as the same point in the contour C, but traversed in the opposite direction. So negative C is the point set of C, so it's the same points, however they're traced out in the opposite direction. Then we'll see that if we took the integral of f over the curve negative C, that would be equal to the negative of the integral of f over the contour C. So if we reverse the direction of the contour, that would put a minus sign in front of the integral. Fourthly, we can break up a contour into pieces. So if we have a contour C, which is made up of contour 1 plus contour 2, C1 plus C2, then we could evaluate the integral of f over C by first evaluating the integral of f over C1 and adding it to the integral of f over C2. So we use this fact when the ending point of C1 is the starting point of C2. So now let's evaluate some contour integrals. First I want to define the contour. So let C be the right hand half of a circle. So the right half of the circle absolute value of z equals 2. So this would be the circle centered at the origin with radius 2. And we're going to go from z equals negative 2i to z equals 2i. Let's look at a picture of this contour. Looks like this. And I want to trace out this contour from the bottom up to the top. So C can be defined by the following function. So if I use theta for my parameter, so typically when the parameter defines an angle, we use theta for the variable. So the circle centered at the origin with radius 2 can be parameterized by the equation 2e to the I theta, where theta now will go between negative pi over 2 and positive pi over 2. So for this contour, I'm going to evaluate the integral of z bar over this contour C. So on C, the point z bar will be equal to the conjugate of 2e to the I theta, and the conjugate of 2e to the I theta would be 2e to the minus I theta. So since z is given by 2e to the I theta, we can differentiate, and we use dz equals 2, we're taking the derivative with respect to theta, we get 2i e to the I theta d theta for the differential dz. So on this contour, we see that the contour integral of z bar dz will become the integral from negative pi over 2 to pi over 2 of 2e to the minus I theta, that's the z bar, and then dz is 2i e to the I theta d theta. Now the e to the I theta and the e to the minus I theta will cancel, and we will just get 4i for the integrand. This equals the integral from negative pi over 2 to pi over 2 of 4i d theta. So 4i is a constant with respect to theta, so when I differentiate, I get 4i theta. We evaluate that at theta equals pi over 2 and negative pi over 2. So we get 4i times pi over 2 minus negative pi over 2. So pi over 2 plus pi over 2 is pi, and we would just get the value of 4 pi I for this integral. So the integral of z bar dz for the contour C equals 4 pi I. So in the next example, I'm going to take an integral over a circle centered at the origin with positive orientation. So we took an integral in the previous example of a semicircle centered at the origin. Now I'm going to let C be a circle centered at the origin. With radius capital R with positive orientation. So it's going to be traversed counterclockwise. So C can be defined by the following parameterization. Z of t equals capital R e to the I t for t between 0 and 2 pi. And we're assuming that capital R is a positive real number. Now I'm going to evaluate the integral of 1 over z over this contour C, so over a circle centered at the origin. And we'll see that the answer doesn't depend on the radius r. So to use our parameterization, we see that on C we have z equals capital R e to the I t. So if we differentiate, dz will be r I e to the I t dt. So we differentiate with respect to t on the right. Then our integral 1 over z becomes the integral from 0 to 2 pi. So 1 over z would be 1 over r e to the I t times dz, which is r I e to the I t dt. Now see the factors of r cancel, the factors of e to the I t cancel, and I'm just left with the value of I in the integrand, which I can pull out if I choose. So I times integral from 0 to 2 pi dt, and the integral of 1 will just be t, so I get it evaluated at 2 pi and 0. And as I mentioned, this is independent of the radius r. So if I plug in 2 pi for t, I get 2 pi I. And if I plug in 0 for t, I just get 0. So this integral equals 2 pi I. So this is an interesting fact that if you have any circle centered at the origin with the radius r with positive orientation, that the integral of 1 over z over this circle will equal 2 pi I, no matter how large or small the radius r is. So in this next example, we're going to show that the value of a function over a contour depends on the contour. So I'm going to evaluate the integral of f over two contours with the same starting and stopping point, and we'll show that the value of the integral changes. I'm going to write two contours, both starting at the origin 0 and ending at the point 1 plus I. So the first contour will go from 0 up to the point I, and then to the right over to the point 1 plus I. So I'm going to call this contour C1. And then the second contour is just going to be along a diagonal line straight from the origin to the point 1 plus I. So this is contour C2. So I'm going to integrate a function over these two contours and show that the value of the integral changes. So I'm going to let C1 be the polygonal line starting at the origin, and so let me label these points. So the point I I'm going to call point A, and the point 1 plus I I'm going to call point B. So C1 will be the polygonal line OAB for the origin to A, then to B. And I'm going to let C2 be the line segment OB from the origin to the point B. And we're going to evaluate the function f over these two different contours. We'll now evaluate the integral of f over C1 and the integral of f over C2, where f of z is going to be defined by the function x squared plus I y squared, where x and y are the real imaginary parts of z. So when I evaluate the integral of f over C1, I'm going to break this up into two pieces. I'm going to first evaluate the integral over the line segment OA, and then along the line segment AB. So let's look at a parameterization for the line segment OA. OA can be represented by z equals 0 plus IY, where y changes from the value 0 to 1. Along this line segment OA, x is always 0, and y goes from 0 to 1. So along this line segment OA, if z equals IY, then the differential dz will just equal I dy. Now the line segment AB can be represented by the parameterization z equals x plus I. Along the line segment AB, the y coordinate is always equal to 1. So z equals x plus I. Now x is changing from 0 to 1. y just equals 1 along this path. So then for along the line segment AB, the differential dz will just equal dx. Then the integral of f over c1 will equal the integral of f over OA plus the integral of f over AB. And now using the parameterization, the integral of f over OA would be the integral from 0 to 1. Now f of z is x squared plus y squared, and along this path x is always 0. So 0 squared plus y squared, and dz is going to be I dy. The integral of f over AB will be equal to the integral from 0 to 1. Now, along this curve, y is always 1, so we get x squared plus I times 1 squared. So we just get x squared plus I, and then the dz is just equal to dx. So the first integrand, we have I squared y squared, so I'm going to rewrite that as minus y squared. Now when we anti-differentiate, we'll get negative y cubed over 3, evaluated at 1 and 0, plus the antiderivative of x squared is x cubed over 3, plus ix, again evaluated at 1 and 0. And so y cubed over 3, when I evaluate it at 1, I get minus 1/3. And when I evaluate it at 0, I get 0. When I evaluate x cubed over 3 at 1, I get positive 1/3 plus I times 1. And then when I plug in 0, I just get 0 plus 0. So the minus 1/3 and the positive 1/3 cancel, and I get a value of I. So the integral of f over c1 equals I. Now let's take the integral of f over the contour c2. c2 is just the straight line from the origin to the point 1 plus I. So c2 can be represented by the parameterization z equals x plus ix, because on this diagonal line, the y-coordinate equals the x-coordinate. So z equals x plus ix, where x goes from 0 to 1. And if z equals x plus ix, then dz will equal dx plus I dx. And if I factor out a dx, I can rewrite this as 1 plus I times dx. Then the integral of f over the contour c2 will equal the integral from 0 to 1 of x squared plus y squared, but the y-coordinate is going to equal x. So it's x squared plus x squared, and then dz becomes 1 plus I dx. You'll notice that the term x squared plus ix squared, I can factor out an x squared from both terms, and I get another factor of 1 plus I. So I'm actually going to factor out both factors of 1 plus I. So I get 1 plus I quantity squared times the integral from 0 to 1 of x squared dx. And when I anti-differentiate, I get x cubed over 3. So we get 1 plus I, the quantity squared, times x cubed over 3, evaluated at 1 and 0. And this gives us 1 plus I, the quantity squared, times 1/3. minus 1 plus I, the quantity squared, times 0. So we just get 0 for that second part. But 1 plus I, the quantity squared, would equal 1 squared plus 2I plus I squared, which is minus 1, all over 3. And so the plus 1 and the minus 1 cancels, and I get 2I over 3. So the point of this example is to show that although C1 and C2 had the same initial and final points, the integrals of f along these two contours have different values. This just illustrates the fact that the contour integral depends on the contour. So notice that C1 and C2 have the same initial point and final point, but the integrals are different. So the integrals of f along C1 and C2 have different values. Now, observe that we could make a simple closed contour by traversing this triangle. We could write a contour C as C1 followed by C2 traverse in the opposite direction, so that would be minus C2. So C1 minus C2 is a simple closed contour. Where we start at the origin and go to A, then to B, and then back to the origin. And we can evaluate the integral of f over this contour. It would be the integral of f over C1, which was I, and then it'd be the negative of the integral of f over C2, so it would be minus 2I over 3. So I minus 2I over 3 would be I over 3. Now we point out that the integral of f over this simple closed contour equals I over 3 because in future lessons we'll see that if f was an analytic function and f was analytic inside a simple closed contour C, then we'll see that the integral of f over C would always equal 0. So since we're not getting a 0 value for the integral of f over this contour C, we know that the function f is not analytic, which we can verify also by the Cauchy-Riemann equations. So this next example of a contour integral will involve a branch cut. So recall that a branch cut is a line or a part of a curve that is used to define a branch of a multivalued function. So our multivalued function is going to be z to the power of 1/2. So in general, a contour integral can involve a point on a branch cut of the integrand but typically we want to avoid branch cuts and we don't want to integrate over a contour that crosses a branch cut, but in this example we're going to have a contour that starts at a branch cut. So just the starting initial point is on the branch cut. So to show this, we want to define the contour C. Let C denote the semicircular path given by the function z of t equals 4 e to the I t, and t is going to be between 0 and pi. So this would be the upper half of the circle centered at the origin with radius 4. We start at 4 and go to negative 4. And we'll see that the function z to the 1/2 is going to be defined with the branch on the positive real axis. So our positive real axis is going to be our branch cut for our integrand. For the integrand, we're going to let f of z be z to the 1/2, and recall that we define this as e to the power 1/2 times the log of z. And so the log function is multi-valued, so that's why the function z to the 1/2 is multi-valued. But we're going to restrict this to the branch with absolute value of z positive and the argument of z between 0 and 2 pi, which is the branch of the multi-valued function z to the 1/2. So this function, if we define the branch cut on the positive real axis when the argument is 0, we see that the contour C has an initial point right on the branch cut. So notice that F is not defined at the initial point of the contour. At the point z equals 4. However, we're going to show that the integral of f along this contour still exists. So as we'll see, the integral of f over c still exists. And the reason is because when we parameterize f, we'll get a function that is continuous from the right at t equals 0. So when we evaluate this line integral, we're going to look at f of z of t times z prime of t. And for z of t equal to 4 e to the I t, we get 4 e to the I t to the power 1/2, so that's your z to the 1/2, times the derivative of 4 e to the I t with respect to t will be 4 I e to the I t. And so we can simplify this. We're going to have the square root of 4 times e to the I t over 2 from the first factor. So we get square root of 4 e to the I t over 2 times 4i e to the I t. If I pull all the constants out front, the square root of 4 is 2, so I get 8i, and e to the I t over 2 times e to the I t. I can add those exponents and I'll get e to the I times 3t over 2. I'm going to write this using Euler's formula, so we can write e to the I 3t over 2 as cosine of 3 over 2 plus I sine of 3t over 2. We get 8i times the quantity cosine 3t over 2 plus I sine of 3t over 2. And when I distribute the 8i, I'll get this as a minus 8 sine of 3t over 2 plus 8i times cosine of 3t over 2. So I've written f of z of t times z prime of t in its real and imaginary parts, and we'll see that this function is continuous from the right at t equals 0. So if we took the limit of this expression as t goes to 0 from the right, we get that the limit exists, and so the function is continuous from the right at t equals 0. So we see if we take the limit as t approaches 0 from the right of f of z of t times z prime of t, we can evaluate this by direct substitution. We get minus 8 times sine of 0 plus 8i cosine of 0. And this just simplifies. Sine of 0 is 0, cosine of 0 is 1. So this just simplifies to 8i. So if we defined the value of f of z of t times z prime of t at t equals 0 to be 8i, then that function will be continuous. So then if we define its value at t equals 0 to be 8i, the function f of z of t times z prime of t will be continuous on the whole closed interval t is greater than or equal to 0 and less than or equal to pi. And so now if we have a continuous function on this closed interval, we can evaluate the integral. So then the integral of c to the 1/2 over the contour c, we'll define it as the integral from 0 to pi of f of z of t times z prime of t, which we wrote as 8i e to the I 3t over 2 dt. And I'm going to write it in this form because we can find an antiderivative of this function. So 8i is a constant, but the antiderivative of e to the I 3t over 2 would be 2 over 3i times e to I 3t over 2, evaluated at t equals pi and t equals 0. So I can do some simplification. I can cancel the i's, and I get 16 over 3 for the constant out front. And when I evaluate this at t equals pi, I get e to the 3 pi I over 2 minus the evaluation at t equals 0, so I get e to the 0, which is 1. Now, e to the 3 pi I over 2 is negative I, so I get 16/3 times negative I minus 1, the quantity. And if I pull out a factor of minus 1, I can write this as minus 16 over 3 times 1 plus I. So although we have to be careful when the initial or the end point of a contour is on a branch cut, we can still evaluate the integral.